Today we will discuss the next topic, that is the robot localization. Okay, so navigation, that is the most challenging competence required of a mobile robot. So here we are addressing only the mobile robots. Okay, the stationary robots, they are basically not having this field of navigation. Navigation here means navigate, move from one place to another. So the success in navigation requires success at four building blocks of navigation. So what are the four building blocks? First one, that is perception. So the robot must interpret its sensor to extract meaningful data. Means the initial part, that is from the sensor, it will try to sense the surroundings. Okay, then next building block is the localization. So the robot must determine its position in the environment. So using the data extracted from the sensors, the robot can determine its position. The next block is third block, that is the cognition. So the robot must decide how to act to achieve its goal. Okay, means some other position which we have given. So the robot has to move from initial position to the final position. So the robot should be able to determine its initial position accurately. Okay, after that it will move towards the goal position. Okay, and the last one is block is the motion control. So the robot must modulate its motor output to achieve the desired trajectory. So here we will discuss some of the blocks here in detail. So first one, that is the localization. So if one could attach an accurate GPS, that is a global positioning system. Okay, so GPS sensor to a mobile robot, much of the localization problem would be obviated. So the GPS would inform the robot of its exact position. So this very common application is in our mobile phone as well. We can switch on the GPS and we can determine our position. Okay, the existing GPS network provides accuracy to within several meters. Okay, so this could be a disadvantage of the GPS based system. So it is unacceptable for localizing human scale mobile robot as well as miniature mobile robot such as the desk robot and the body navigating nano robots of the future, means very small size robots. So if the accuracy is within a few meters, okay, then the location given by the GPS, okay, that is having errors. Okay, also we can say that in the outdoor applications, if the robot has to move a long distance, in that case the GPS based sensor system is okay, fine, like for long distance. But if it is in for the indoor application, just one room to another room, the robot has to move, in that case the system won't be suitable. So furthermore, GPS technologies cannot function indoor. Yes, the same thing which just we discussed, or in obstructed areas, and thus they are limited in their workspace. Means alone GPS system is not sufficient for large size robots, long distance traveling. These are sufficient, but not for small robot indoor applications, small distance to be traveled. Okay, now further during the cognition step, a robot will select a strategy for achieving its goals. If it intends to reach a particular location, then localization may not be enough. Okay, the robot may need to require or build an environmental model, a map that aids in it planning a path to the goal. Okay, means robot has to move from one position to the another position or the initial position to the final position. Okay, then it has to build a map, the trajectory or the path which it has to follow. So in its memory. So once again, localization means more than simply determining an absolute pose in the space. Okay, it means building a map, then identifying the robot's position relative to that map. Position, mostly the initial position and the final position. Then the path which it has to follow. Okay, then clearly the robot sensors and effector play an integral role in all of the above forms of localization. So it is because of the inaccuracy and incompetence of these sensors and effectors that localization poses difficult challenges. Okay, so here different type of challenges, okay, or the difficulties, issues, they come up due to the errors imposed by the sensors and the effectors. So we will discuss these of the inaccuracies caused by the sensors. So first one is the sensor noise. So sensor are the fundamental robot input for the process of perception, and therefore the degree to which sensor can discriminate the world state is critical. So sensor noise induces a limitation on the consistency of sensor readings in the same environmental state, and therefore on the number of useful bits available from each sensor reading. Often the source of sensor noise problem is that some environmental features are not captured by the robot's presentation and are thus overlooked. Okay, so these are the basic errors which are caused in the sensor. So taking an example, a vision system used for indoor navigation, okay, in an office building may use color values detected by its color CCD camera. So we will also be discussing this computer vision in our coming topics. So when the sun is hidden by clouds, okay, so what the example here is that the computer vision that is being used by the robot and using the different type of colors, we have programmed the robot to identify the position or the any type of location, okay, when the light is not there, sufficient illumination is not there, okay, the this computer vision or the camera that may not be able to clearly identify the color. Okay, in that case the signal that will be having noise or that won't be accurate, it will not give a clear state data to the computer. So this type of error, that is the sensor noise. So next is sensor aliasing. So the problem known as sensor aliasing is a phenomena that human rarely encounter. So the human sensory system, particularly the visual system. So here also a common example will be taken from the vision or the computer vision, that tends to receive unique inputs in each unique local state. Okay, so or commonly we can say that every different place looks different. So the power of this unique mapping is only apparent when one considers situation where this fails to hold. So now example is the like the moving through a unfamiliar building and it is totally dark. So when the visual system sees only black, one's localization system quickly degrades. Okay, so it means that the data which is being received, that is not giving a clear idea. So another example is that of a human-sized maze made from tall hedges. So maze is there, very difficult to analyze the position, initial and the goal position. Okay, because every location looks like the similar in the maze. Okay, then consider a narrow beam rangefinder such as ultrasonic or infrared rangefinder. So this sensor provides information in a single direction without any additional data regarding material composition such as color, texture, and hardness. Even for a robot with several such sensors in an array, there are a variety of environmental states that would trigger the same sensor value across the array. So formally, there is many to one mapping from environmental states to the robot's perceptual input. Thus, the robot's percepts cannot distinguish from among these many states. Okay, so another thing is that the higher the number of sensors, more will be the accuracy in the data received, because the different type of sensors will give different type of data. Then all of that can be compiled in the memory, and an image can be built. Yes, sir. Now coming to another error induced due to effector noise. So mobile robot effectors introduce uncertainty about future state. So therefore, the simple act of moving trends to increase the uncertainty of a mobile robot. So there are of course exceptions. So using cognition, the motion can be carefully planned so as to minimize this effect, and indeed sometimes to actually result in more certainty. Furthermore, when the robot's actions are taken into concern with careful interpretation of sensory feedback, it can compensate for the uncertainty induced by noisy actions using the information provided by the sensors. Okay, next it is important to note that from the robot's point of view, this error in motion is viewed as an error in odometry, or the robot's inability to estimate its own position over time using knowledge of its kinematics and dynamics. The true source of error generally lies in an incomplete model of the environment. So in odometry, that the wheel sensors that are studied there, and dead reckoning, so also the heading sensors. The position update is based on proprioceptive sensors. The movement of the robot sensed with the wheel encoder or heading sensors or both is integrated to compute position. Because the sensor measurement errors are integrated, the position error accumulates over time. Thus, the position has to be updated from time to time by other localized mechanism also. Okay, because initially error, then after the movement, the error will keep on integrating. Okay, also we can say that joints are also there. A minor error in one joint, then it will further go on integrating with other joint. Okay, finally there will be a large uh, error induced in the position or in the movement of the robot. So many sources of automatic errors, from environmental factors to the resolution. So they are listed as so limited resolution during integration, like the time increment, measurement resolution, and all that. So misalignment of the wheels, that is deterministic. The next, the error, that is uncertainty in the wheel diameter and in particular unequal wheel diameter. Then variation in the contact point of the wheel, and another error, that is unequal floor contact. So this could be due to slipping, non-planar surface. So they can also induce the errors. So some of the errors might be deterministic, systematic. Thus they can be eliminated by proper calibration of the system. So we can remove this type of errors. However, there are still a number of non-deterministic or the random errors. They still remain in our system. From geometric point of view, one can classify the errors into three types. So range error, that is integrated path length, the distance of the robot's movement. Okay, that is some of the wheel movements. Then next is turn error. So they are similar to range error. Okay, but for turns, difference of the wheel motion. And last is drift error. That is difference in the error of the wheels leads to an error in the robot's angular